Howdy, everybody. Just here for day 16 of Advent of Code. Today was a fun one. I actually was able to do it last night for the first time in a little while, just because I had the time to do it. Um, I thought it was a great problem, but again, thanks for all your feedback. I got some ideas on better ways to improve some of my previous ones. That's always cool to hear. Um, and Again, I'm always happy to see what you guys are doing, so feel free to share that with me. And with that out of the way, let's get into the problem. So if you remember yesterday, we were working on lenses. The algorithm didn't have to do with lenses, but the idea is you're putting lenses in boxes to help focus a beam. Well, you've now turned that beam into like a laser or whatever. And the problem you're trying to do is you want to like trace where the beam goes. If it starts right here, like where the beam goes when it hits all these objects, right? So they give you some descriptions of the way things work. Maybe it will. I did make a copy of this one, and so maybe I can just show you really quick what they look like. Right. So if the beam is starting right here and moving in this direction, it's going to hit this. And these parallel line ones are splitters. And so if it hits the splitter like this, then it's going to split the beam this way and this way. And so you can imagine then the beam is now going to follow its way down here, all the way down here. And then it's going to split this way and this way. And eventually it hits one of these angled ones, right? If it doesn't hit these parallel ones perpendicular to them, it will just go through it. So this beam is going to continue to travel through it, hit here, then hit here, then hit here, and so on and so forth, right? You can see this one, then it splits here and goes down here, up here and here. And so as they're splitting, you now think the way to think about it is you're now kind of creating like multiple beams that are going through this path. And the idea is you want to keep track of those and eventually find out how many of the tiles were energized. And by that, what they mean is how many of these touched, how many of the points on the grid touched a beam, right? So all of these ones down here count, all of these count, but like it's possible that like this one didn't get touched, right? If you look at it, like they have a final solution for this, like this is where the beam went. If you trace it and split it and trace all the splits and stuff like that, and then these are all the points that the beam actually touched, the hash ones, and that's a signal that or if you count all those up, that's like the solution to the problem, right? So after you've traced the beam everywhere, you count all the places the beam touched, unique places, right? And then that's your total to the solution. So obviously the actual solution is much larger. You'll have to do a lot more like tracing. This is actually one you could potentially do by hand, right? Because it's just you're tracing stuff through. I guess all of them you could do by hand. That's a weird way to say it, but now that I'm thinking about it, is as I'm drawing this out, at least for the small one, it'd be relatively easy for you to kind of like trace this out. The large one might be harder to keep track of, but anyway, that's the general idea of the thing. Is can you take this beam that you created last time and trace it through this grid and then find out how many points it touched on the grid when you're done. And because of the splitting, I think the first thing that someone might like run into is like feel kind of bogged down by how much there might be to track or how much there might be to do. And so a lot of times with problems like this, when you're splitting, you're branching, the way that I like to think about it is like, let's just start with the basics. Like, what are the basic things that we need to know? And then we can build upon those basic things to like help us get to a solution. So obviously we're going to have a beam and it's going to trace through the grid. Like, what information do we need to know about that beam, right? So we're going to have some beam, and what do we need to know about it? We obviously need to know its position, right? Its current position, like that it's tracing through, like where is the beam right now? So it's going to start right here. But we also need to know what direction it's going, right? And so they say it starts going in to the right. So we also need to know its direction, right? And then what we can do is just kind of reason about, at every given position, how do we alter the beam's position and direction, right? So it's right here, it's moving right. That's pretty simple. It's on a dot, so it's just going to keep moving in its same direction, right? So a dot would be just like keep going, right? I apologize for my writing. Now that it's right here, we now have hit a splitter. So we want to ask ourselves, what do we want to do when we've hit a splitter? More importantly, what do we do when we've hit a splitter that's in this direction? So we can say, okay, well, if I'm at this position, I'm on a splitter and I'm going, so if how do I do this? If there's a dot, it's this. If it's, I didn't do that very well. So if it's a dot, it's this. If it's this, and we're going left or right, now we want to do something else, right? We want to change our direction. So the direction should go to down, for example, and create a new beam with the direction going up. Okay, that's enough. That's enough attempting to draw when I've been typing for the last 25 years of my life, or attempting to write. That's the way I like to think about it, is like, if I can just focus on that part of it, just it turns out like most of the solution is, hey, given a beam, its position and its direction, wherever it is on the map and wherever it's going, I can kind of enumerate all of those different things and then just pick one of them based on where I'm at, right? So if I'm here and my direction is going this way, I know now my direction is going to change going this way, and so I should move it up here. And if I'm I don't know, here and going this, I go this way, and now I'm here, I've hit the splitter, and so my previous direction, or my current direction, is still down, so I know I'm going to hit it, and that means I need to create a new beam going this way and a new beam that goes this way. And if I can think about that, like those simple steps, then now I've like broken down this problem into something much more easier. I can just kind of do a loop that goes that just every place the beam is, match it up with its current direction and what's there, and do some logic to move the beam to where its next position would be. And then I can do that recursively until I like hit one of the edges, go out of bounds, something along those lines, right? Some point that I would stop at doing that. And so that was the solution I came up with, and we'll look at it in code. There's a couple things to think about though. Obviously you want to track where the beam has touched for your energized count. And so I just did that with a hash set, right? It's like every position the beam touches, I just add it to the set. And then when I'm done, I can just do, s.lane, and that will give me my energized position. The other thing I wanted to talk about really briefly is that I didn't really pay attention to is cycles in the beams. When I first got done with this logic and ran it the first time, it did not occur to me that the beams might cycle. And so I ran it and it just kept running. And I'm like, whoa, what's going on? And as I looked at it, it turned out that the beams would form cycles. And so you just go on forever. So the other thing you want to track, maybe I can show you that, in particular in the test case, imagine this one right here, this part right here. If you trace this out, when it hits here or it hits here and splits, it goes like this, 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 and this goes down. This goes up, up, this way, or sorry, this way. Where is the cycle? Why can I not find it in this one now? It was this one that was the cycle, but why can I not see it? Maybe I need to trace it backwards. Let's see if we can find it again. This, 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 this. There it is. There's the cycle. So do you see how you kind of make this big loop, but then it hits again, this same position, and you just kind of do this thing forever. You go this way forever. So that was something that I had to keep track of. So what do you do to solve that? Just like we talked about yesterday, obviously if you have a beam that you've seen before that has the same position and direction, you can, you know that you're going to recurse, or you're going to cycle back to something you've done before. So we just keep track of a set of beams that we have positions and directions, and if we ever see one of those, we know we can stop. Okay. And finally, the third thing that you want to think about in these cases is you say to yourself, okay, well, I know I can traverse this beam, and I know I can track like every place it's touched. I now know I can track cycles. The last thing you want to do is, hey, well, what happens when I split, right? How do I deal with splitting of it? So if you just kind of keep it, and the way that I did this was, I'll just keep a queue of beams. And if I ever split, I'll just add to the queue. And I'll just keep processing all the beams until there's no beams left to process in that queue. So there's the fourth part of it, right? So why am I describing all this stuff? Just again, like when you're thinking about any programming problem, it's much easier to solve the problem if you decompose it into like its constituent pieces, right? So you say to yourself, well, at a very base level, what am I trying to do? I'm trying to track this beam, its position and its direction. And based on where it is, I need to like do some logic to manipulate where the beam goes next. And I can just kind of track that. And then you say, well, I need to track the energized places where it touches. I can do that with a set, right? I also need to track if I've ever hit a cycle. Okay, well, that's not too hard. I already know how to do these parts, so I can just check to see if I've seen that beam state before, and if I have, I can be done with it. And then lastly, you want to like deal with splitting beams, and you say, well, what is a split beam? It's really just two beams that are doing this same stuff. So what if I just add it to a list, right? And I think this is where understanding data structures you have available to you and breaking it down to the components really can help you with solving these Advent of Code problems, but also any problem in general, right? Imagine like a very naive approach where you didn't have all this stuff and you were trying to like think about, okay, now that I've split a beam, I now need to like trace through all the beams and keep track of all of them as they're adding up. You could do that, but it would be complex, right? And instead you can say, oh, well, I know I can use a queue for the beams and just queue them up and process them later after I get done with my current beam, right? Same thing with tracking those cycles, right? Is like a naive approach would be, oh, I have to I have to go check and see, I'll track all the places that I've been, and then I can like backtrack and see if I've hit another place, right? Just the ability to use a set to track your beam positions will help you a lot there. So again, what I hope you'll just get out of what I ended up doing with the problem was, can I break this like more complex problem into its component pieces, and then from there, each of those pieces will help me come to a complete solution. So what does all of this look like in code? Let's check it out. So what do I need to know about the beam, right? Obviously, I need to know its direction. And so I'm just going to track that with an enumeration, up, down, left, and right. And I also need to know its position in the grid, right? So what am I going to do with that? I'll just do a point, and I'll put it, where is it on the XY positions? For the point, I implemented the add feature, so we could just do some simple math on it. But then here's my beam structure, right? So I'm going to track the beam. And like I said before, what am I interested in? Its position and its direction. Okay, so I wrote some helper functions, right, for the beam to kind of help me through my logic. First, I want to know if I've gone out of bounds, because I know if I've gone out of bounds, the beam is off the grid. It's never going to come back on. So that's just a simple checker to say, hey, am I out of bounds? Notice I'm using I32 here. That's because you're doing a lot of like subtraction and addition, and it felt easier just to do that. Instead of like subtracting like these minus ones here, things. Anyway, the other thing besides out of bounds that I need to know is, how do I move a thing forward, right? I originally did the directions as like delta points, like, -1, 0, 1, 0, things like that. I chose the direction up and down because it looks better in Rust's match logic. I don't think there's any wrong with using like the adjacent type things. You'll see that in a lot of code where like, what are the adjacent positions? And those are the deltas of like, up, down, left, and right. I just chose the direction. So I just need to create a move forward function that translated an up direction into what? And what does that do? It changes the Y direction one less. Same thing. And then the same thing with down, left, and right. Okay, so those functions again were mostly just to clean up the logic so it looks a little bit nicer in the actual algorithm that we'll go to in a second. And so finally, what do we need? We just need a grid, the grid that comes from the thing. It didn't feel like you needed to do any special parsing here, like in NOM or anything, because again, you're just given a grid. Which we've seen quite a bit the last few days, right? And the simplest way to do that is just to iterate over the lines, and then for each of the lines, iterate over all the characters and collect them all up. Okay, so finally, the big part of the program is this calculate energized function. And so you can see what part one is doing. I create my new initial beam position, which is starting at the origin and going right. And then I just call calculate energized, and that is what gets me to the solution. So let's go over that. Again, I want to track which ones I've touched, so I'm going to create a hash set for that. I also want to keep track of where we split it, and you could do this in a vector or whatever, so any kind of list. I have just used vecdqs before because you can push and pop kind of like you would a normal like queue. So we're going to create that list, and then we're going to add our initial beam to that list. And what do we do with that? We're going to just, this is Rust syntax for, right? As long as I can pull something off the top, keep processing it. So I'm just going to loop through all these continually until there's nothing left on the queue. And then again, the one thing that I missed the first time I was doing it that caused me to stare at my screen for a minute while it was processing, I need to be able to track cycles, right? And so we're going to keep a scene list, the beams that we've seen before, and keep processing it, or stop processing when we get to that point. So again, I'm just going to loop through all the beams that I put on the queue until I've processed them all. And what do you do with a beam? This is also a while loop, right? You're just going to keep doing these things. You're going to keep traversing until there's two conditions, right? Either the beam has gone out of bounds, or the beam's current state is some state that you've seen before. And so that's all you're doing for each of the beams. Process it until you get out of bounds or you've seen some previous state before. So the rest of this is that processing logic, right? So what do we want to do with each beam state? And this is this part that I was talking about right here, right? We're at some position on the board. It doesn't really matter where it is. We don't care where the beam, well, it does matter where it is because we want to do it, but each position entails the same logic, I should say. And what is that logic? Well, first we want to add it to our energized list. So now we're tracking that, okay, we've touched this place. We know that should be part of our energized list. And we also want to mark that we've seen this position, right? So if we ever get back to this position again, we know that we've seen this before and we don't have to continue. And then the rest of this is I use Rust's match feature. The idea is I'm going to test the position on the grid and the direction the beam is going. And that's just a fancy way of saying I want to know what direction I'm going. Am I going left, right, up, or down? And I want to know my what this thing is right here. So is it a dot? Is it this? Is it this? Is it this? Is it this? Right? These different things. I want to, right? If you think about how my beam is going to change, it's going to change based on some product of these values and these values, right? Obviously, if I'm at this position, everything's gonna be different if I'm going this way to it, this way to it, this way to it, or this way to it. And so it's just like this Cartesian project. Some of them will do the same thing, and so I don't have to worry about those. But I do want to handle the special cases for those positions. And so what are the special cases? Okay, so if I hit a pipe, and I'm going right or left, that means I've hit the pipe this direction or this direction. I want to create a new copy going up, and then I just want to change my direction to down. So the way to think about it is I've hit this thing, I'm going to create a new one that's going up and push it up to its next position, and then I want to change my direction to go down. And you'll see later, after all of this, I call beam move forward. It turns out that all of these call beam move forward. So I just kind of leave that to the end. Maybe I can make this note here. Will cause the beam to move forward in its possibly new direction, right? And so I just kind of left that out for all these special match cases. Okay, so again, if I'm hitting this pipe going left or right, I just need to create a copy of it and move it up, and then I just change my own direction to down, right? And notice I'm pushing back onto my beams list. So eventually I will get to it in this beams pop front right here, this part right here. But I'm not going to worry about it now. I'm just going to deal with this right here. The other case is if I hit this dash and I'm going up or down, now I have to split, but it's the same as the above, but now I'm just making a clone going left and putting that on my stack. And then I'm making a clone and then I'm moving my direction right. The rest of the cases are just change direction, right? So if I'm hitting this slash and I'm going up, I know I'm now going right. And all of these cases are the same thing. You can kind of visualize them, right? Like again, so like this example, if I'm here and I'm going right, I know I'm now going up. They all kind of create like these 90-degree angle turns. And these are the only special cases, right? Every other case, like for example, if you're doing this, if you're on this position and you're going left or right, the problem said, oh, that's a pass through. So all of them, the rest of them is just move forward, right? So I don't have to do anything for them. And then here I can move forward. And that's it. That's the logic of the whole internals of it. So it turned out not to be super complicated. But again, I want to stress, like, I feel like the complexity of it is, and what this problem was good at illustrating is, can you take a problem that at face value, like if you're just trying to mull about it in your head, may feel complex, and break it into its component pieces of, hey, I just need to know a beam, its position and direction, and then I can do some logic to determine where it should go next. And then can I track some additional stuff I need to track to get me to my solution, right? And you're building up these layers of solutions to eventually come to a complete solution. So how does this thing all end? Well, once we've moved the beams all around, eventually we run out of items on the beam and we're done, and then we can just return the energized lane, and that will give us our answer, right? So if I run it, oops, you can see it gives me my answer. Part 2 actually takes a couple seconds. If you actually run it in like optimized mode, it's only 260. I do actually think, though, there are some optimizations for it. And I'll maybe I can explain what part 2 is. Once you solve this thing and you get the answer, they're now like, okay, well, what if can you tell us what the actual optimal entry point is, right? So we started at this position going this way, but what if we started at this position and went this way? Or what if we started at this position and went this way? Or this position and went this way? And you do that all around the edge of the grid, right? So for each position, can you pick the directions that are like perpendicular to one of the ends, and go in those directions, and then find the one that produces the most energy beam, or the most energized cells in the thing. It didn't, to me, part 2 seemed like okay, now that you've solved this problem, can you just like solve it a bunch of times? And so that's literally what I did. You can see my for loop is, I solved part 1 starting at beam position 0. This code down here is basically just iterating over all the edges and checking all those cases and tracking the max value and then returning that. I actually did spend some time, for people that are here watching interested in the Rust stuff, I spent some time trying to like come up with an iterator that would do all of these at once, and it looked pretty ugly. At least the ones I got, it was a lot of like, do this and then chain this with this and stuff, and it ended up not looking very good. So I just kept it in a for loop. If you happen to have solved it in a fun way where you can, like, I don't know, if there's some way for you to create an iterator over ranges that would just do these outside edges, I would love to see that. That would be cool, because that's what I kind of tried to do that for a little bit, but ran out of time. And when I had initially implemented it, it actually looked uglier in my opinion than just doing these 2 for loops, right? So the 2 for loops are basically just, I'm going to go this way, and then I'm going to go this way through all the values and see if through all the edges and see which one is the max. And it does take a little bit of time, but I don't know that it again, I think the way that they describe the problem's solutions is like, it's like an average piece of hardware in the last 10 years should be able to solve it within a minute or 2 or something like that. There's some I don't remember the exact values. So the fact that it took a couple seconds felt like, oh, this was a sufficient enough solution. I should say that, though, that because you're calculating these, there is some potential to do some optimizations. And what I mean by that is, right now we're only tracking the beam cycle. If we've seen a beam before, and if we have, we know we're done. If you were potentially tracking something like, oh, I know if I'm at this state, it colors like all of this stuff. And so this is where you'd have to do some kind of dynamic programming. But you could say, like, if you did some kind of dynamic programming where you knew that this caused all these to energize, you could potentially reuse that on all of them, right? Because if you think about a lot of the starting states, like this starting state here going this way, this starting state here going this way, this starting state all going this way would hit it. This starting state going here, going this way, this one, all of those eventually hit this beam or hit this position and would cause like this cycle to occur. So you could potentially do some dynamic programming there where you were tracking that, oh, if I hit this state, I know I produce this energy state, and that might help you come to a faster solution. Again, I kind of felt like 1 second was a fast enough, so I stopped there. If you did happen to implement it that other way, or maybe some other way where you can short circuit, again, essentially what you're doing is you're just short circuiting this, is like, because all of them are the same, you maybe track some like state here, something like this. You're tracking some state here and you're reusing it in all those places. It would give you like a faster solution. So if you did that, I would love to see it. I've run out of time to do it. So there you go. There's my day 16. Again, I think this one was, in my mind, can you break up a larger problem into its smaller component pieces? You'll see this a lot, especially if you go into previous days. You'll get instructions that are like fairly complex. And what you have to just say to yourself is, oh, I'm just going to deal with like one instruction at a time and solve that part of it. And then I can like bring them together in the end. So look for ways to do that. Obviously, I appreciate all you guys watching it. I love the feedback you've been giving me. Keep that up. And again, I'm doing my stuff. I'm trying to post all this on the Reddit mega threads for the solutions. If you have yours, I'd love to see it. Just like kind of ping me, and so I know to look at yours and check it out. If you found some better way to do something or some optimization to my code too, I'd love to see that as well. So that's the cool thing I think about what I'm trying to do here, and the ability to use something like YouTube is we can all kind of share our solutions and collaborate together and all become, smarter, I guess, better at this stuff. So it's fun to do that together and do that with all of you all. So there you go, everyone. Have a great day, and we'll talk to you tomorrow.